Cool. Thanks a lot for being here today for more CMB. There's never enough CMB. And so today, the topic of this lecture, we will stop talking about what happened at the last scattering surface, and we'll start talking about what happens as the CMB photons travel from the last scattering surface all the way to us today. And so these are often called secondary anisotropies, where the primary anisotropies would be the ones at last scattering. But I don't think you should take it to mean that they are less important. I think there's a lot you can learn from these secondary anisotropies. And these anisotropies that are imprinted as the photons travel from the last scattering towards us are both a source of signal, if you're trying to learn about the large-scale structure closer to us, and they're a source of noise and bias, if you're trying to look at the early universe. And so they're both a signal and a foreground for studies of the last scattering surface. Okay, so we covered what the CMB is and the temperature monopole, the temperature fluctuations, the polarization fluctuations. Today will be secondary anisotropies. And what I hope you will learn from this lecture is that the large-scale structure of the universe, which you have heard a lot about, gets imprinted onto the CMB in many, many different ways. And so there's many ways in which you get to learn about the large-scale structure in ways you couldn't have done by just looking directly at galaxies. Hopefully, you'll get a good idea of what the extragalactic and galactic foregrounds are, meaning the ones that come from our own Milky Way versus the ones that come from outside of it. I'll tell you more about the so-called Sunyaev-Zel'dovich effects and how CMB lensing works and how we measure it. Okay. So to go back to the big picture I showed in the very first lecture, with this timeline of the history of the universe, with the hot Big Bang on the left, and us all the way on the right, 14 billion years later. And we talked in the past few lectures about how when we look at the CMB, we see the baby picture of the universe, we see the initial conditions of the universe. But of course, for us to see the CMB photons have had to travel all the way to us. And during that journey of 14 billion years, several things happened. One of them we sort of talked about already with this idea of scattering at reionization. And we mentioned last time that about 6%, 5 or 6% of the CMB photons get scattered, Thomson scattered on their way towards us. And part of that Thomson scattering occurs not just at reionization, but at late times in the gas around galaxies and clusters. And so I'll tell you a lot about this. And loosely speaking, I might call this a shadow of the gas. So once you have ionized gas around galaxies or clusters, they have free electrons which can scatter the CMB. And if they scatter the CMB, they will imprint a small shadow onto the CMB, which we can observe. And so this shadow tells us about how much gas is there. Another thing that can happen, or that happens to CMB photons on their way towards us, is gravitational lensing. And so you've heard quite a lot about this from David and from last week about how lensing works. But basically, the gravitational potentials from the large-scale structure pull on the photons and deflect their paths. And so the CMB temperature that you see here, perhaps you should have been seeing it there if its path hadn't been deflected. And lensing is very interesting to me because what it does is it tells you how much mass is there. It tells you the size of the gravitational potential. And so it allows you to map all the matter in the universe, not just the visible one, but also the dark matter. So these are two sort of big types of shadows or CMB secondary anisotropies that are imprinted on the CMB. And something else to mention is that the cosmic microwave background is not the only light out there at microwave frequencies. A lot of things emit at microwave frequencies. And so you will see just light being emitted by galaxies, including our own, at these frequencies in different ways. But the sort of metaphorical picture I want you to keep in mind when you think about the CMB secondary anisotropies is that the observable universe is like a shadow theater, where you have the puppets and the shadows and it tells a story. And here the backlight is this cosmic microwave background, the first light from the Big Bang. And the protagonists, the main characters in this shadow theater, are the large-scale structure and the galaxies in front. Really not the stars. It's unfortunate that there are stars on this drawing. I think a lot of people are getting very interested in the cosmic microwave background. This is my daughter learning about the primary anisotropes and then the secondary anisotropes. So I hope you'll be as interested in it as she is right now. So this is nice and all, but what does it look like in practice? And so here's a cosmic microwave background map on only a few degrees on the side, measured by the Planck satellites. And what you can see is you can see those hot and cold spots that are roughly about a degree in size. And again, this is the size of the acoustic scale. So this is determined by the sound horizon and those baryonic acoustic oscillations. And the blur, the graininess you see here is noise in the Planck measurement. But with ground-based telescopes that are larger in size, you're able to increase the resolution, and you're also able to reduce the noise. And when you do, you might end up with a map like this. So this is a map from the Atacama Cosmology telescope. And with that, it's already an outdated one from 2020. And so when you observe the same CMB, but with a higher resolution and higher sensitivity, you see a few things that pop out. So you still have sort of those hot and cold spots, but now you have some little dots here and there. And again, with the conventional color scheme in CMB maps, red means hotter or more light. And so those red blobs you see here are actually microwave emission from AGNs, so active galactic nuclei at the center of galaxies, and dust emission from the dust inside star-forming galaxies. So the idea is you have stars that form in a galaxy, they heat up the dust around it, and the dust emits then at those microwave frequencies. But you might also notice that there's some little blue dots. So again, some small objects, but which appear less hot or less energy in the CMB photons that we see in this direction. And this, at this frequency, is actually the effect of the Sunyaev-Zeldovich effect, which I'll tell you more about. And these are actually galaxy clusters whose shadows have the effect of lowering the temperature we see in the CMB. So with the kind of resolutions that we now have with CMB experiments, about arc minute for something like ACT, we start to be able to sort of resolve individual objects like galaxy clusters. And in fact, if you've done any amateur astronomy, you can start to image some of your popular amateur astronomy targets with CMB maps. So again, from this 2020 ACT map, which is already outdated, you can observe objects like the Helix Nebula, which you can see in a small telescope from a clear sky location. And you can see, individual galaxies. So really, the CMB is not just, CMB experiments are not just measuring those big degree-sized blobs from the less scattering surface. With high resolution, you get to see a lot more. So listing now the main extragalactic imprints on the CMB. So those are often thought about as foregrounds, again, because they make it more difficult to look at the CMB. So when you're looking at CMB frequencies, around 100 gigahertz or around a few millimeters of wavelength, you don't just see the CMB. You see dust emission from star-forming galaxies. And this combined together, this dust emission from all the star-forming galaxies in the universe, is what we call the cosmic infrared background. So CIB, cosmic infrared background. I'll say a little bit more about this in a moment. And then you see this thermal SZ effect, which I just mentioned. And so these are shadows from the gas around galaxy clusters. So every little blob you see here is effectively a galaxy cluster or a galaxy group that's casting a shadow on the CMB. Radio point sources. So those are often the results of AGN or galaxies that are bright in radio, and you're seeing the tail of that spectrum in our millimeter frequencies. And then there's this other type of Sunyaev-Zeldovich effect, the kinematic Sunyaev-Zeldovich effect, which I'll tell you more about in a moment. But to give you a sense of how much they matter in terms of being a foreground or being a problem for when you care about the primary CMB, what I'm showing you here again is this dimensionless CMB power spectrum, so L squared CL as a function of L. And again, the large scales are here, small scales are here. The gray line that you see here with the wiggles and going down should be very familiar by this point. So this is the primary CMB power spectrum. And all the colorful lines you see here are those different foregrounds. And so you see, again, cosmic infrared background in green, thermal SZ in blue, kinematic SZ from clusters and reionization in red and orange. Some of these foregrounds are correlated because the same galaxies that can live in clusters and imprint SZ might have dust that emits towards the cosmic infrared background. And so you have the correlation between TSZ and CIB. And again, those radio point sources. To give you an idea of how these foregrounds compare to the typical detector noise of CMB experiments, this dashed line you see here is the typical level of detector noise, so noise from your instrument as opposed to from the sky that you get with something like Actor Simon's Observatory. And so in the other power spectra, yeah, so that's a good question. The other power spectra, because they typically trace the matter density, if you were to measure their power spectrum in 3D, you might see something like this as a function of k, p of k, and you would have a 2 halo term that's basically the linear power spectrum with the BO wiggles. You might have a 1 halo term, which tells you about how the sources are distributed within the halo. And then you might have a shot noise, which is saying that the individual galaxies might be just Poisson sources. So if you were to measure the 3D power spectrum for these sources, you might be able to see the BAO wiggles. But when because the sources come from many different redshifts, you get, yeah, exactly, it gets diluted. So in the Limber approximation, which has been talked about, you get something like this. And so basically the different K modes get converted to different L modes due to the different distances. And so that sort of smooths out all this thing. And
we see this in galaxy distribution.
Exactly, yeah. Yeah, so I think it depends also on the depth of your averaging. So if you're able to do a narrow shell in galaxies, you won't lose it too much. But a lot of these things are for very broad redshifts. Yeah, yeah, thanks for the question. Mm-hmm. Right. Oh, yeah, so that's a very good question also. So why does the CIB looks like it continues going, whereas the TSZ goes down? Oh, are you comparing CIB and CMB? Oh. Right, so the CIB is this green curve here, and the TSZ is this blue curve that goes down. But your question is a good one. Why do they differ? Right, and so first I should say, because here you're plotting L squared CL. If you were just plotting CL, you would see that the green curve here would basically be flat at high L. And this flat curve is exactly this shot noise here. So typically when your sources are point sources for the purpose of your resolution, and if they're close to Poisson distribution, distributed on small scales, you'll end up with a power spectrum that's flat, so a white noise. And this is what you see for the CIB because the emission comes from individual galaxies, and those galaxies might be arc-second in size, whereas your resolution is arc-minute. So they're very much point sources. On the other hand, for TSZ, for example, the signal comes from extended galaxy clusters. And so these galaxy clusters have a profile. They're not point sources. And so you do get this one halo term, but not the shot noise. And so this is why the TSZ power spectrum goes down, but the CIB doesn't the same way. Oh, sorry, this curve here, right? Oh, yes, sorry. So this is the CMB. So the CMB, so this is in log-log. So you see the acoustic peaks, the odd-even height asymmetry. You see that amplification from radiation driving, and here you're seeing the silk damping that kills the CMB power spectrum on small scales due to that diffusion. Another feature you might see is that the power spectrum should actually go down faster. This component you're seeing here is actually extra power due to lensing of the CMB. And I'll talk a bit more about this. But yeah. Yeah, that's a really good question. And I think I'll talk more about this. But the short answer is the KSZ changes sign depending on the velocity. And the velocity on average is 0. So when you correlate KSZ with any field that doesn't change sign with velocity, you will get 0 by symmetry. But I'll say a bit more about this. Hopefully that'll help in a few slides. At high L, yeah, at small scales. Mm-hmm. A typical what, sorry? Peak. Yeah, so I think it might be hard to see on this figure, but the TSZ cross CIB does have a downturn, and the downturn is intermediate in speed between green and blue, sort of as you would expect for, yeah. So yeah, one way you can think about it is, so here you see TSZ and CIB are about the same in size in terms of power spectrum, whereas the TSZ cross CIB curve here in purple is quite a bit smaller. And so you can think of this as a correlation coefficient of a few percent between TSZ and CIB. Mm-hmm. So maybe I'll just go through and say a bit more about TSZ and CIB throughout the slides, and hopefully that'll help clear up your questions. But yeah, thank you. And so, yeah, one more question. Mm-hmm. Right. So actually, I should have said this plot is at a fixed frequency. So this is what a sky map would look like at 150 gigahertz, which is roughly usually our main CMB frequency. So when you have multiple frequencies, and I think I'll say a bit more about this, maybe not too much, you can combine them together if you know something about the frequency dependence of these various components versus that of the CMB. And in this process of combining the different frequency maps, you can actually lower the level of these foregrounds. So this one is kind of like a worst case scenario. This is what happens if you just take a map of the sky at 150 gigahertz and don't do any cleaning. Mm-hmm. Yeah, no, this is what you see at 150 gigahertz. So I think that's pretty accurate. They cross at 3000, but what you can see is this is the crossing between CIB and CMB. If you add all of these foregrounds together, that curve goes up. And that's what this black curve is. Another thing you might notice is there's many orders of magnitude on this plot. So, you know, it looks like black and gray touch each other here, but at this point you still have quite a big difference. Mm-hmm. Right. So here, I haven't shown Milky Way foregrounds. I'll do that in a moment, but I might not show their power spectrum. So the Milky Way is the one for which it matters very much where you're looking. Of course, if you're looking closer to the Milky Way, the foreground there will be much more important. For these extragalactic foregrounds, it doesn't depend too much where you're looking. But yeah, we do worry a lot about all these foregrounds. And indeed, like you mentioned, so the power spectrum in these extragalactic foregrounds is extremely dominant on small scales. And so the way we try to reduce them is by using multiple frequency data, like you said. But that only works to a certain extent, and it gives you an idea of the challenge if you're trying to measure things like the CMB at such high L by how much you have to reduce those foregrounds can be a very large factor. Another challenge is that these foregrounds are typically non-Gaussian. So the primary CMB is very close to Gaussian as far as we can tell. These foregrounds are not because they trace the large-scale structure and halos and galaxies in the universe, which are not a Gaussian field. So they are non-Gaussian. Their modeling is often very uncertain because it involves a lot of astrophysics. Their frequency dependence can also be uncertain in certain cases. They're correlated with each other because they all trace the large-scale structure, and they're also correlated with lensing. So all this makes these foregrounds quite a big challenge. Okay, so these were extragalactic foregrounds in temperature. In polarization, life turns out to be a bit easier, and you can see a number of the foregrounds have dropped out of this map because most of them, like the thermal and kinematic SZ, are not actually polarized. And so the only foregrounds, extragalactic foregrounds that we expect to be polarized are some of these point sources. And that's due to a synchrotron radiation around magnetic fields, can impart a polarization to the light. And you can have a residual dust polarization from dust grains that would be not spherical and aligned together. But life is easier in polarization because the polarization fraction for these two foregrounds is only of order 1%. And the result is, if you compare the EE power spectrum in polarization to the typical level of foregrounds, they cross at something like L of 5,000 or beyond. And you can compare that to something like more like 3,000 for temperature. So in polarization, extragalactic foregrounds, so the ones that don't come from our Milky Way, are expected to be less of a concern. There's another thing that helps. So their power spectrum is less. There's fewer types of foregrounds. Their statistics is often simpler because they're often very well modeled by just uncorrelated point sources with random polarization orientation. And so the Poisson statistics is a pretty good model for them, which means we have a pretty good idea of the non-Gaussianity of these foregrounds. Whereas for things like thermal SZ, for example, you need to model more than just the Poisson shot noise, and so life is more complicated. I'm just highlighting a study of these foregrounds that was led by Frank Chu, who's currently a postdoc at Stanford, and has been thinking a lot about these foregrounds in the context of how it biases CMB lensing. Moving on to Milky Way foregrounds as opposed to extragalactic foregrounds. Now, once you look at a map of the sky for those Milky Way foregrounds, you clearly see a dependence on where you're looking. And so this is the Milky Way plane. There's pretty much no hope of seeing the CMB through this because the emission is so bright. And the distinct emissions that we see from the Milky Way, we separate them based on their spectrum as a function of frequency. And so here you have in those units what the CMB black body looks like. And you can compare that to this emission here in green, which is the sum of synchrotron emission, so electrons spinning around magnetic fields, free emission, which is basically Bremsstrahlung. An electron slows down on an ion, and the process emits light, and this anomalous microwave emission. And so put together, they have a frequency dependence like this. So a typical frequency we mentioned just a few moments ago was around 100 or 150 gigahertz is typically where we observe the CMB. And you can see it's no coincidence. It's sort of the sweet spot between the bright foregrounds from radio and Bremsstrahlung, which are very bright at lower frequencies, and where dust emission from the Milky Way starts to go up. So at low frequencies, radio emission, synchrotron free are a concern. At high frequencies, dust emission is the main concern. Those foregrounds are also most important on the larger scales, so the lowest L in your map. And you can see this because the feature you're seeing here, you're seeing them on the scale of basically the whole sky. So those foregrounds are concerned at low frequencies, at high frequencies, and mostly on large scales. Yes, question. Mhm. Oh, from space versus Earth. Right, sorry. And so the question was, will those foreground maps be different depending on whether you're observing from the ground or from space? And so these components here are emitted by the Milky Way itself. And so this is the sky you would see whether you're on the ground or in space. However, there are a lot of advantages in being in space. One of them is you do not suffer from the atmospheric emission. So in optical astronomy, a concern with the atmosphere is mostly seeing, meaning your resolution gets degraded by turbulence in the atmosphere. In cosmic microwave background observations, the main concern is emission from the atmosphere itself. So things like water vapor emits in the microwave. And that emission is also polarized to some extent. So by being on the ground, you suffer from the atmosphere's emission, which is a source of noise, and which also makes it very hard to observe at many different frequencies. So the place where space really helps is because you don't have the atmosphere, you can observe in many different frequency bands. And this is what something like Planck did, and something like Lightbird aims to do. So yeah, it does help to be in space. Mm-hmm. Mm-hmm. Yeah, we have good maps of the cosmic infrared background, and those maps are typically made using the fact that the spectrum in frequency of the cosmic infrared background is that of thermal dust, and it's pretty different from the CMB and the other foregrounds. So that lets you extract the CIB. However, the reason why this map says dust plus CIB is that these are both thermal dust emission, and so it's actually pretty hard to distinguish Milky Way dust from extragalactic dust. Something that helps is you can look at your CIB properties as a function of galactic latitude. If you find that they change a lot, it means that your CIB map was pretty contaminated by Milky Way. Cool, so these are the foregrounds in temperature. We have some idea of the foregrounds in polarization. And like before, when you go to polarization, a number of these drop out and synchrotron remains. Again, this is electrons orbiting around magnetic field lines, which gives them a certain direction of motion and therefore emit with polarization. So I won't say too much about these polarized foregrounds from the Milky Way, other than they are a key limiting challenge for searches of B modes. And they can easily be confused with the primordial B mode signal. So I think that's most of what I was going to say about the foregrounds. So again, it's important to think about, what are the different types of foregrounds, at which frequencies do they dominate, and on which scales they dominate. And if you have an idea for the frequency spectrum of these foregrounds, then you can use observations at different frequencies to try to disentangle the foregrounds from the CMB. I'll talk a bit about the CIB and the TSZ in more detail in a moment and show you how, in some cases, we think we know very well the frequency dependence, and in some cases, not so much, which makes it harder to use multiple frequency data. But I thought I would now switch gears from sort of the bad news part of all these things, how they make life hard for measuring the CMB, to the good news part of it, which is all the things you can learn about the large-scale structure from them. Question? Yeah, so if you were to observe the CMB, at one of these frequencies, but really at any frequency, when you observe the CMB, you see a very bright emission along the galactic plane. And so typically what's done is this emission is being masked. So you take your map and you throw out all the pixels that are close enough to the galactic plane, and you might keep only something like 60 or 70% of the sky for your data analysis. Otherwise, that would completely mess up your paraspectrum. Thanks. So there's different things you can do, but the typical approach is to not replace them with anything. but take into account that your map was masked. And so when you are estimating the power spectrum of a map, if that map has been masked, it modifies the power spectrum you measure, but in a way that you can correct for if you know the mask. Mm-hmm. Mm-hmm. Right, so you have your estimator for the power spectrum. I guess it's what David had written on the board. You know, you're measuring all the ALMs of that map and taking the average of their squared modulus. But now the map is just a map where all the pixels here have been replaced by 0, I guess. Maybe that was your question, yeah. So when you mask them, you replace the pixel values by 0. And that modifies the power spectrum, but in a way that you can account for. Cool. Right, so you will sometimes see maps of the CMB where you can actually see the CMB through the Milky Way. Most of the times, these maps are actually made by in-painting, which means you have actually masked the Milky Way and set it to 0, and then a fake CMB has been in-painted, meaning they have drawn a realization of a Gaussian random field consistent with the rest of the actual measured map. But these maps are only used for visualization purposes. We do not use those maps for science. The in-painting process in other circumstances can actually be used usefully for science in the case of lensing. But in that case, you do not in-paint such a large fraction of the sky. You might just in-paint individual point sources. And we can talk about this more. One more question? Deal with, sorry? E2B leakage. Oh, yes. So that's a more challenging question, and I think there's a number of ways to do that. There's those pure E and pure B mode decompositions, and there's other approaches as well. So I'm less expert in this, but I think there's a number of methods, and there's a lot of subtleties there. Mm-hmm. All right, so moving on to all the things we can learn about the large-scale structure from the CMB. So I have a fairly busy slide here, but it's sort of the one-slide summary. It'll be in the slide deck. If you keep this slide with you, you'll never be lost with the CMB secondary anisotropies. And the reason I put this slide together is because there's many different effects that you'll hear about. Some have to do with gravitational potential. So there's the effect of lensing, which you've heard about. There's the effect of integrated Sachs-Wolf that I told you about last time, and which a lot of people would call a secondary anisotropy because it doesn't come from the last scattering, it comes from in between. There's the Riesz-Sciama effect, which is the same as ISW, but on scales of individual halos. So there, the gravitational potential evolves with time because the halos are still forming and accreting. There's an effect called the moving lens effect. I probably won't talk about this. And then there's a number of scattering effects. One is screening, the same thing we talked about for reionization, where CMB photons can get scattered. But now that same screening can occur around galaxy clusters or galaxies when you have free electrons. There's the kinematic SZ, the rotational kinematic SZ, the turbulent kinematic SZ, the thermal SZ, the relativistic thermal SZ, polarized scattering, and then you have a lot of other effects that are multiple scattering. So a CMB photon will not scatter just once, but twice. And so I think it's easy to get lost and a bit overwhelmed with all these effects. But I think something that helps me think about them is that they are all the products of these dimensionless number. And so these dimensionless number, these key parameters, are properties of the large-scale structure. And all these effects are just some product of these parameters. So the first one I'm listing here is sort of the typical lensing deflection for the CMB, about 1 arc minute or 10 to the minus 4 in radians. And that's a number that tells you about sort of the total mass of your halo, how much mass is in there. So that's one property that's imprinted. The other one is how much does the gravitational potential change over time along the path of the photon. And so that's pretty much this integrated Sachs-Wolf effect or the Risch-Schama effect. And so on large scales, it tells you about dark energy, for example, as we talked about. But on small scales, it tells you about how much or how fast a halo is accreting matter, and its potential is deepening. Tau, the optical depth to Thomson scattering, we talked about the mean tau between us and the CMB through reionization. But every time you look through a cluster, you get an additional optical depth from the gas, the ionized gas in this cluster. And so if you can measure the tau, the optical depth of individual objects, you measure how many free electrons are there, and therefore how much gas is there, and therefore how many baryons are there, which can be very hard to do in other ways. The next parameter is the electron temperature. So how hot is your gas around galaxies? And that's typically a small number. And so if you can measure this, you learn about the thermodynamics of your gas around galaxy halos, which can be very important. The other parameter is the various bulk velocities of your gas. So how is the overall halo moving towards or away from you or to the side? What are the typical rotational velocities in your halo? What are the typical turbulent motions? And finally, the last sort of few dimensionless parameters don't have anything to do with the large-scale structure. They're just the typical fluctuations in the primary CMB. But that number will enter for some of the secondary anisotropies. And so, to give you an example, the size of the effect of lensing is just this lensing deflection. For ISW, as we talked about, it's how much the potential changes. The so-called moving lens effect combines the lensing deflection and bulk velocity. And TSZ, KSZ, etc., are various products of optical depth of your halo times different properties of the halo. And so in the next hour, my goal will be to tell you a bit more about some of those scattering anisotropies and some of those potential anisotropies. And so I'll start with the scattering, but if there's any question now. Okay, so let's start with the gas shadows and those scattering anisotropies. One reason I think they're so interesting is that we've all seen those beautiful images of galaxies with spiral arms from Hubble and galaxy surveys. And in fact, this little white dot here is a Hubble image of a galaxy. But what you may not suspect when you look at a galaxy is that you're really seeing the very, very tip of the iceberg. And galaxies and galaxy groups are actually surrounded by large gaseous halos where most of the baryons, most of the ordinary matter actually resides. So only 5 to 10% of the ordinary matter is in the form of stars. So when you see the beautiful starlight from galaxies, you're seeing almost nothing of the ordinary matter. I think the Andromeda galaxy, which is one of our nearest neighbors, which you can see with the naked eye or with binoculars, if you could see all the gas around it, it would actually take about 60 degrees of the sky. So it would fill a huge amount of sky. So that's one reason why it's interesting to see those shadows. More precisely, what I'm showing you here is from a hydrodynamical cosmological simulation, the Illustrious simulation. And what you're seeing in blue is the distribution of dark matter. And so the bright blobs are dark matter halos. And what you're about to see in green and red are the gas density and temperature. And if you look at the simulation, you see all these explosions around halos. So it's like a real fireworks going on in the cosmic web. And basically, what those explosions are a supernova, so dying stars that explode, as well as violent injection of energy and momentum from active galactic nuclei, so supermassive black holes at the center of galaxies. And these processes together, these explosions, are what in galaxy formation we call feedback in galaxy formation. So this is a process which pushes the baryons outside of the halos, and by doing so, it regulates the formation of stars and galaxies. So it's a negative feedback in galaxy formation. The gas cools, you form stars, the stars explode, they push the gas out, which limits the ability for other stars to form. But the problem is that the amplitude of these feedback processes in galaxy formation currently is our biggest theoretical uncertainty in the whole process of galaxy formation. And part of the reason is we don't know how powerful these feedback mechanisms are because it's hard to measure how far out the gas was pushed or how much energy was injected into it. So this has sometimes been called the missing baryon problem, the fact that once the baryons are pushed out of the halos, they're often too diffuse and too cold to be seen in emission, and so they're hard to find. And so for a time, this was called the missing baryon problem. We now know that the baryons are there, they're just a bit farther out. Yes?
Is it known at least if it's the supernova or the AGN is the higher contribution or?
Right. So I think it's mass and redshift dependent statement. But for mass, basically in lower mass halos, so like individual galaxies, typically I believe the supernovae are dominant. And in more massive environments like clusters, the AGNs are dominant. And so then when you go to intermediate mass, a bit of both is happening. So yeah, you might, if you want to fully understand galaxy formation, you might need to understand both of these mass regimes. And there's other effects as well that I'm less expert at that also have an impact on the baryons, things like cosmic ray winds and things like this. And so that's a problem for galaxy formation, the fact that we don't know where the baryons are, and so it's hard to constrain how powerful those feedback processes are. It's also a problem if you want to do cosmology with large-scale structure data. And so I'm sorry, for me, LSS is sometimes less scattering surface and sometimes large-scale structure. And the challenge here is that we're going to have cosmic shear, so galaxy lensing measurements from experiments like Euclid, Rubin, or Roman observatories. And these measurements are going to be basically percent precision measurements of lensing. But the baryons are 15% of the total matter. And so if you don't know where 15% of the matter is, you're going to have a hard time modeling percent precision data in lensing. And so currently, this phenomenon is called baryonic uncertainty, the fact that on the scale of group and cluster halos, we don't exactly know where the baryons are. And the way people deal with it currently is to just throw away the lensing information on small scales. So you measure lensing, you have information down to the scales of individual halos, very precise measurements there, but you don't know how to analyze it because you don't know where the baryons are, and so you just throw away this information. So if instead you could measure how far the baryons are pushed out, one, you would learn about feedback in galaxy formation, and two, you would really allow us to learn much more from upcoming lensing measurements. And for me, that's really the motivation for looking at those scattering anisotropies, those gas shadows. So I've been pretty loose in calling them gas shadows. Maybe I need to now finally tell you exactly how they work. And so these are called the Suniev-Zeldovich effects. And they are scattering effects. So if you imagine a gas halo around galaxies or clusters, typically this gas is hot and fully ionized. And so you have a lot of free electrons in the gas, and these free electrons are moving around. They're moving around for two reasons. One, because the gas is hot, and so the electrons are just moving randomly very fast. And two, because the gas halo itself might have a bulk motion. So when a CMB photon comes in and Thomson scatters off of an electron, several things happen. So the first effect, if you ignore the motion of these electrons, is screening. So a very similar effect, actually the same effect that we talked about for reionization, except now instead of scattering at reionization, you scatter in the gas around halos. And so that effect, that change in temperature is proportional to optical depth, or how much gas you have, and just what was the original temperature fluctuation you would have seen without screening. So screening tells you just about how much gas you have. But again, because the electrons are moving, there's two additional effects. And one way to think of it is when the CMB photon bounces off a moving electron, it's kind of like a tennis ball bouncing off a moving racket. If the racket is moving towards the ball bounces off with more energy. And if the racket is moving away from the ball bounces off with less energy. So you can think of this Thomson scattering as, this is like a moving mirror, and this photon is bouncing off a moving mirror, and so a Doppler effect is going to occur. So Doppler effect, these two thermal and SZ, thermal SZ and kinematic SZ, I think of them as Doppler effects. But in one cases, you have one bulk velocity, so the whole halo is moving. And so all of the electrons are moving mirrors at the same speed, and so they all impart the same Doppler shift on the CMB. And so when you Doppler shift a black body by a certain amount, you get a black body with a different temperature. And so the KSZ effect is just a change of temperature, no change in the spectrum. And it's a Doppler effect, so it's proportional to V over C and proportional to how opaque those electrons are. If you had no electrons, you would have no effect. And so naturally, this is proportional to tau. So this effect is again interesting because if you think you understand the velocities, it tells you about tau and therefore the electron number density. If you think you understand the electron density, you can use it to learn about velocities on large scales, which is also very interesting. And then the other effect is thermal SZ. So again, you have a photon bouncing off a moving mirror, which is your free electron. But now we're talking about thermal motions. And so those motions are random in direction. And so each electron with its own motion will turn the CMB it sees into a CMB at a different temperature. But an electron might scatter the CMB into a black body at higher temperature or lower temperature. And when you average together many different black bodies, what you get is no longer a black body. You get a spectral distortion that's called a Y distortion. And so that has a well-known frequency dependence that we can compute from first principles. And it still depends on how opaque your gas is. And now at lowest order, it goes as V over C squared as opposed to V over C, because the mean V over C is 0. With thermal motion, half of the electrons are moving towards you or away from you. And so this effect tells you about how many electrons, so density, times their mean square velocity, which is basically their temperature. So thermal SZ tells you about density times temperature of the gas, and density times temperature is thermal pressure. So if you can measure screening and KSZ and TSZ, you have measured the gas number density and the gas pressure. If you have both at the same time, you can infer the temperature, and so you've learned a lot about the energetics of that gas. So right. So if I look at the sky, you're saying in different directions. If I have a halo there, then these effects will occur there. And if I don't have a halo there, this effect won't occur. And so this is why all of these effects will imprint an image on the CMB, which looks like kind of a map of where the clusters are. Thanks. And so now I'll tell you a bit more about each of these effects in this order. And the reason I'm going in this order, in part, is because here they're ranked in terms of typical size. And if you're trying to get an order of magnitude for how large these various effects are, all you need to do is go back to this slide, get these typical numbers for the different parameters, and again, notice that the different effects are just products of those. Okay. Mm-hmm. 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 Right. Yes, so physically, that's really what it is. And so here, for example, would be a way to look at it for the thermal SZ, a change in the intensity of the light as a function of frequency. So why are we expressing it in terms of temperature? That one is more related to how the measurements are made. So indeed, the measurements are just intensity integrated within a certain frequency band. And those we typically convert linearly to Rayleigh-Jeans temperature. There's some subtleties there, but we convert it to temperature. What makes this conversion useful is that now for the CMB, you should get the same map at all frequencies. So it's basically just rescaling linearly the intensity in a way that would give you the same map at all frequencies for temperature, but nothing physical there. Yeah. And so on average, when you look at this effect, it turns out the CMB photons typically actually gain energy in those random Doppler boosts. And so what this does is that if this dashed line here was the initial CMB black body you would have seen in the absence of SZ effect, after the CMB photons have Compton scattered or Thomson scattered on those free electrons, the new spectrum is something like this. And this looks like a black body at a slightly different temperature plus distortion. And so when you look at the change in intensity, you get this curve here in solid. And it's a very characteristic curve. It's one that you can compute from first principles. So in temperature units, the SZ effect is given by this frequency dependence, where x is the frequency in units of CMB temperature, times, again, density times temperature. And the frequency dependence you can compute from first principles, and it's plotted here. What's remarkable about that frequency dependence is, one, it is known pretty much exactly from first principles, which is very helpful for extracting the signal. And two, it is negative at frequencies below 220 gigahertz and then positive. This is what you can see here. You know, if I shift the overall spectrum to the right, at low frequencies, I have reduced the intensity, and at high frequencies, I have enhanced it. And so in particular, if you make a map of the sky at 220 gigahertz, you will not be affected by the TSZ. And if instead you make the map of the TSZ at frequencies in these two ranges, you'll have found that the TSZ effect has changed sign, whereas the CMB hasn't. And so that lets you distinguish the two. Mm-hmm. Yeah, it's an overall blue shift, but not one that's just a change in the temperature, because that would just take a black body into a different black body. This is a blue shift with a weird shape. Yeah. Okay, and so as I showed you on this initial ACT map, for massive clusters, you can see the TSZ effect by eye. You can see, if you're at 150 gigahertz, you can see this temperature decrement. And this is why the little TSZ dots looked blue. They looked like a decrement in temperature. But you can also measure TSZ effect for much less massive objects, like individual galaxies inside galaxy groups. And in that case, often you will not have the sensitivity to detect it for each object individually. And so what you can do is a method called stacking. So just to show you, if you take one of those, this is a luminous red galaxy from BOSS, and this is its image in Hubble. And again, galaxies are very small. This one is about 1 arc second in size, whereas the resolution of the map is closer to arc minute. And so this square here is actually the size of a single pixel in my CMB map from ACT. So if I take an ACT map around the location of this galaxy and I look at the temperature map, what I see is basically nothing, just noise. And that's because the TSZ signal is way too small for me to pick it out on one object. But if I instead start adding the signal from many, many galaxies, as I add the maps at the locations of many more galaxies, slowly the noise gets averaged down. And eventually you see this dark blob. And that dark blob is the thermal SZ profile, meaning it's the density times temperature profile around the galaxies. And so it shows you that while the individual galaxy fits in the central pixel of that map, the gas is extremely much more extended. So this is just an example of how stacking can let you reveal these galaxy shadows when they're too faint by statistically averaging many objects. So this is a measurement I made in 2020, but since then, Henry Liu, who's a grad student at Berkeley in the US, has improved my measurement a lot, and the signal to noise is now a lot larger than it was before. One big challenge in those measurements of thermal SZ that is already apparent in these images is when you stack on a typical temperature map, I would have expected to see something like this, not something with a hole at the center. So what is this hole at the center? I would expect there's more gas and hotter gas at the center. I don't expect less thermal SZ at the center. And what's happening here actually is that the galaxy itself that I'm stacking on has some thermal dust which is emitting light. And as we've seen, the thermal SZ effect, typically at CMB frequencies, is a negative effect. But the dust emission is positive, and so it cancels it out. And so this is what you're seeing here at the center, the dust emission canceling the thermal SZ signal. And thankfully, the galaxy is small, whereas the gas is very extended. And therefore, on the outskirts, I see the gas in SZ, and at the center, I am biased by dust emission. Okay, so this is all I was going to say about the thermal SZ effect. And I will now move on to talking about this kinematic SZ effect. And here the subtlety is that the effect depends on the bulk line-of-sight velocity of your halo because of that Doppler effect. And half of the halos will typically be moving towards you and the other half away from you. So they will have different sign. And so if I simply stack my maps at all these positions of halos, the signal will average down to 0 because the velocities can be positive or negative. So if I want to avoid this cancellation, there's several things I can do. The methods that we've been using is called velocity reconstruction from the galaxy density field. And I don't know if you have heard about BO reconstruction yet, but this is a very similar idea. If you write the mass conservation equation in linear theory, it relates the velocity field and the density field. And if you don't have much intuition for this operator, basically all this is saying is, if I have more stuff here, it's because stuff has been moving towards it. So intuitively, this is all this equation says, conservation of mass. If I have more stuff here, it's because stuff has been moving towards it. But the nice thing with it is that if I have an idea for what the density field looks like from, for example, a large galaxy catalog in 3D, I can perform this operation on the galaxy number density and get an estimate for the velocity field everywhere. And so here's a visualization that was done by Bernardita Ridguachaya, who's a student at Stanford working with me. Each dot you see here is an individual galaxy from a spectroscopic sample. And the colors represent whether we think the galaxy is moving away from you, from us, or towards us, based on this reconstruction process. And so this is the data set I was using in 2020. Bernardita since then has been switching to the DAISY catalog, which is a lot larger and a larger volume. And so you can see that for every single galaxy in this catalog, we have an estimate for whether they're moving towards us or away from us. And thanks to that estimate, we can now stack the temperature map around each of these objects, weighted by the velocities, to avoid the cancellation in the sign due to the velocity changing sign. And so this is the KSE measurement that I led in 2020 with ACT and BOSS. And since then, Bernardita has improved the measurement a lot. And the little blob you see here is the gas density profile around these DAISY galaxies. So this is a high precision measurement of the gas profile from KSE. It allows us to check that measurements that were done on photometric galaxies actually match our spectroscopic sample. The signal to noise is now high enough that we can explore dependencies of the signal based on mass, redshift, etc. And the evolution of our signal to noise as a function of number of galaxies is as expected and makes us optimistic for future galaxy surveys. So this is all I was going to say on the kinematic SZ. I don't know if there's a question on this before I move on to screening.
So I guess this effect is higher than by the earlier side. Because it's right because there we have further gas, right?
Yeah, so the effect will be larger in more massive halos that typically have more gas. And so here we're looking at these luminous red galaxies because they tend to live at the center of galaxy groups. And so by stacking on individual galaxies, we're actually stacking on galaxy groups, which helps our signal. So yeah, the signal scales as the gas mass, which roughly scales as the halo mass. Cool, thank you. Right. Yes. So I have these two axes. Is the question? Yes. So here, this is the scaling of the signal noise as a function of number of spectroscopic galaxy, and this would be the scaling as a function of number of photometric galaxies. And so why is that different? So if you have two galaxies of the same masses, but one for which you don't know the redshift very well, this will affect the quality of your velocity reconstruction. So right, one reason why the velocity reconstruction works so well is because the velocity field is coherent on very large scales. So these are several hundred megaparsec, and along this direction, maybe 50 megaparsec. And 50 megaparsec is roughly the photo Z error for typical surveys. And so if you have a photometric galaxy and you don't know where it is to plus or minus 50 megaparsec, you might give it the wrong velocity, and that lowers your signal to noise. So the rule of thumb is one spectroscopic galaxy is worth 4 photometric galaxies in terms of how the signal to noise scales. Right, and this was used to put on the same plot something like LSST that's photometric with something that's spectroscopic like DAISY. Thanks a lot, yeah. Okay, so finally patchy screening. This is an effect that hasn't yet been detected, though we have attempted it. And again, this is an effect that's a bit unique. So the kinematic SZ changes sign based on the velocity of the halo. And this is what we use to extract it with this stack weighted by the velocity. The screening changes sign based on the sign of the primary CMB. So how does that work? Imagine here a map, a 1 degree by 1 degree CMB map in the absence of screening. So you see those degree-sized CMB blobs. If you have a cluster here and there and there and there, what the screening does is it replaces some of the photons you should have seen with average photons. So if you're looking in this cold area here, the screening replaces some cold photons by some average photons, and so it makes it look closer to the mean. And so if I take a slice through this image, for example, black will be the primary CMB, and the little green blips you see are the scattering by individual clusters. They try to bring the temperature back towards the mean. And as a result, the effect here is positive if the original temperature was negative, and the effect is negative if the original temperature was positive. And in this respect, it's kind of the only secondary anisotropy that changes sign in this way. And so estimators have been derived to take into account this effect. But one has to be careful about important biases due to things like CMB lensing, for example. So still something to be detected. Okay, so I was going to say about scattering anisotropies. I have one slide about the cosmic microwave background, and then I'll move on to CMB lensing, which is really interesting, I think. So here's a cutout of a map of the cosmic infrared background from Planck. And this is I guess the plot I tried to draw on the board here. This is the power spectrum of a typical CIB map. And so again, you have a clustering term, a one halo term, and shot noise. And this map, which looks like completely blended, is the sum of all the thermal dust emission from all the star-forming galaxies in the universe. And you have a lot of these star-forming galaxies, and so when your resolution is 1 arc-minute, you end up with a completely blended image. I guess it's kind of the Olbers paradox. And so being the sum of all the thermal dust emission for all the star-forming galaxies, it contains information about the star formation history in the universe. And so it tells you something about curves like these, which are star formation rate density as a function of redshift, and the fact that it peaks around redshift 2. And so indeed, the peak emission for the CIB monopole is around that redshift 2. So on the CIB, it can be useful in many ways. One, to tell you about star formation rate in the universe as a function of time. It can also be useful because it's a probe of the large-scale structure at fairly high redshifts. And so it can be useful in many ways. Okay, moving to CMB lensing. And this time, the image is actually a cartoon. You do not see such a large distortion around individual galaxies. But the point remains that thanks to CMB lensing, you are able to tell how much total mass is in the halo around that galaxy, which is something you couldn't do by just looking at the starlight. So again, the starlight is 5 to 10% of the total baryons, and the baryons are about 1/6 of the total matter. So when you just look at the starlight, you see very little, and lensing allows you to see all the mass. CMB lensing has become a really important tool for cosmology, and so this is a now slightly old table from the Simons Observatory Science paper in 2018-2019. And this table lists a lot of the the science goals for this experiment. So learning about the initial conditions of the universe and inflation, learning about additional particles in the universe, properties of the neutrinos, dark energy, feedback in galaxy formation and reionization. And if you ask, for how many of these science cases does CMB lensing help, the answer is those. So pretty much all of them. So CMB lensing has become really a crucial cosmology probe if you want to learn about primordial non-Gaussianity, if you want to remove the lensing B modes to see the primordial B modes, if you want to do de-lensing to learn about new particles. The amplitude of lensing tells you about neutrino mass. It tells you about the growth of structure as a function of redshift and therefore dark energy. So a lot to be learned from this CMB lensing. So what is CMB lensing? So again, CMB lensing is the fact that the CMB photons on their path from the last scattering towards you, their paths are deflected by the gravitational pulls from the large-scale structure. And to give you a sense of how large of an effect that is, typical numbers you can have in mind is, again, the primary CMB is degree-sized blobs. And those deflections are very small, of order a few arc minutes. But those small deflections are coherent on degree scales. So you take your map of the CMB, you take a degree-sized blob, you move it by a few arc minutes, and then the next degree, you move it by a few arc minutes in another direction. That's what lensing does. Lensing conserves surface brightness, which means that it doesn't change the temperature of the CMB, it just puts it in a different place in the sky. So the temperature that you see here after lensing is the temperature that you would have seen there before lensing. And the difference between here and there is just this deflection vector field. And in the simplest approximation, which is a very good approximation for CMB lensing, this deflection field, which is a 2D vector field on the sphere, if you want, is actually entirely determined by one scalar function. So it's a perfect gradient of a scalar function, the lensing potential, or equivalently, this lensing convergence. So if you tell me the lensing potential, I can tell you the convergence and the deflection field. If you tell me the convergence, I can tell you the others. Everything is determined by just one scalar function in CMB lensing. I like to think in terms of lensing convergence because it is a dimensionless parameter such that kappa of 1 would be strong lensing, and it's a parameter that's directly related to the matter density field. So what does a typical lensing convergence map look like? It looks something like this. So blue and red are positive and negative convergences. And what you're seeing here really is a projection between us and the CMB of the matter density field. So you're seeing in projection all of the matter in the universe between us and the CMB. And you can see this field varies on very small scales. And if you ask, given this convergence field, what will be the effects on a given CMB map? So here's a simulated unlensed CMB map. And here's the effect of lensing. So I can flip between the two. So that's the effect of lensing. So again, very small deflections of order a few arc minutes, but smooth deflections coherent on degree scale. And naively, if you wanted to measure CMB lensing, what you would have to do is get a map of the CMB after lensing, get a map of the CMB before lensing. You would compare the two, and that would tell you how much deflection has occurred. But of course, in real life, you don't get to see the CMB map without lensing. All you see is the lensed CMB map. And so you might wonder, how can one possibly measure lensing when all you get is this, which by eye looks identical to this. But it turns out those two maps, which by eye look identical, statistically are unmistakably different. There's two ways to think about it. You can say that this map has a form of non-Gaussianity that this one doesn't due to lensing. Another way to think about it is that while this map was statistically homogeneous, this one is not for a fixed realization of the lensing field. And that perspective, I think, is the easiest one in order to understand how CMB lensing measurements work. But I'll just say in words that if you remember, something we discussed when we talked about power spectra and statistical homogeneities is if I have statistical homogeneity, so I'm thinking about flat sky to make things easier. When I take the covariance between two temperature modes with two different L vectors, I get something that's proportional to a delta Dirac of L plus L prime, which means if I choose L and L prime randomly, that covariance should always be 0. So that's statistical homogeneity. In the presence of lensing, what you instead find is that this same covariance quantity is actually proportional to the lensing convergence at L plus L prime. And so this quantity is now no longer 0, which means that this fixed realization of the lensing field has broken the statistical homogeneity of the map. And so because of this, one natural way to then estimate lensing is to just measure those off-diagonal covariances, the ones that should be 0. And if you measure all of the various TL times TL prime for all L and L prime, you will find that they're not 0, and this will allow you to estimate kappa. And this is why in CMB lensing world, people talk about a quadratic estimator. It's an estimator that has 2 power of temperature, and that's because that's the way to measure those covariances between Fourier modes. There was a question. Mm-hmm. Right. Mm-hmm. Yes, so here I've been a bit loose with those two pictures. I've told you, I've said on the one hand, oh, lensing makes the CMB non-Gaussian, or lensing breaks the statistical homogeneity. And the difference is, are you holding the lensing field kappa fixed? And intuitively, you can see how if the lensing kappa is fixed, meaning I always have a massive halo here, then no matter what the realization of the unlensed CMB behind, the CMB you see will always have a weird feature at the center. And so now, no matter what happens with the unlensed CMB, there's a special location in space. And so you no longer have that translational invariance. And so that picture is the one where you assume that this field is fixed, but you're considering many realizations of the unlensed CMB lensing. And you might wonder, why do I get to fix something and take different realizations of the other? In the real universe, I have only one realization of lensing and one realization of the unlensed field. And the answer is a bit the same as how we measure the power spectrum. And if you remember in power spectrum, if I take different L vectors with different directions, they are different independent draws from the same power spectrum. And the same kind of rule helps here. Basically, if I do TL, T big L minus L, and I measure this at fixed L, big L, but for all little l's, this will always be proportional to kappa L. So this is the same equation as above, but I've just shuffled the L's. And what that tells you is if I want to measure a fixed Fourier mode of kappa, I can combine all these different Fourier modes of temperature. And so in this picture, I can think of kappa as being fixed while I'm getting many different realizations of the unlensed CMB. So that helps. Yes?
Why are you writing the multiple as a vector?
Oh, right. It just makes the, I could write it with ALMs, but it just makes the analytical calculations a lot easier in flat sky. Oh, so I'm doing the same thing that I did in the lecture 2, where I'm pretending that I'm cutting a small patch of sky, a small flat patch from my spherical map. You can derive all of lensing reconstruction on a small flat patch of sky, and then it generalizes to spherical harmonics, but the math is just a bit easier. No. I have an actual derivation for this quadratic estimator, but maybe just to make sure I finish on time, I'll cover the rest of the talk. And if people are interested, I can outline the derivation or do it in the Q&A. Right. So that's a really good question. And the answer is it is becoming useful. So it depends basically on the sensitivity of your experiments and how many Fourier modes you're able to measure. And so for something like Planck and something like ACT, the quadratic estimator contains most of the information. And so going beyond the 2 point, you don't gain very much. For experiments where your signal to noise is the sensitivity is low enough that polarization starts to matter, and your signal to noise on polarization is high enough, there you can benefit a lot by going beyond the 2 point. And those are those Bayesian lensing reconstruction or iterative lensing reconstruction, where instead of just saying, I'm going to build an estimator for kappa from quadratic combinations of the map, in that other approach, you are actually writing the full likelihood, where you say, my observed map is the sum of the lensed CMB plus noise. The lensing is perhaps a Gaussian field, and the unlensed CMB was a Gaussian field. So you can write a full likelihood at the map level. And right now, people have figured out a way to explore that likelihood. So both find the maximum a posteriori lensing map, but also actually generate samples of lensing map and unlensed CMB map from that posterior. And for an experiment like with the same noise level as what CMBS4 was planning, you can get a factor of a few improvement in signal to noise by doing this. So a lot of gains. For Simons, I think it's borderline. You will have some improvement. I think enough that it's worth doing, but not enough that it will make the quadratic estimator obsolete. Yeah, thanks a lot. Okay, so I'll just skip through that CMB lensing reconstruction derivation, and I'll just show you the state of the art for measurements of CMB lensing. Yes, question? Mm-hmm. Mm. Mm-hmm. Mm-hmm. It's always the same, yes. Mm-hmm. So I think that's exactly my point, is that in the real universe, I don't get different realizations of the temperature map. I get only one. But my point is that if I want to build an estimator for kappa now, my estimator for kappa can just be the average of those TL minus L, where this is no longer an expectation value over ensemble. It's not an ensemble average. It's just the sum over little else times how many of these modes I have. And so this is exactly how CMB lensing reconstruction works. It's the same idea as when I take these pairs of Fourier modes, they are different realizations of the unlensed CMB, but they all together estimate the same mode of kappa. And so in my head, I can think of it as I have average over realizations of the unlensed CMB at fixed kappa. But in practice, I have only one realization, and that works. Yeah. Mm-hmm. But that's great. That's the reason it's useful. If I had only one L vector, I would be averaging over one thing, and so my noise would be very large. Because I have many, many Fourier modes little l, this estimator is an average over many independent realization, and that's why it works well. But yeah, happy to chat more about this. Thanks for the question. Okay, so this is the CMB lensing power spectrum as measured by ACT and Planck and the South Pole telescope, as well as their combination. And the black line, I believe, is the lambda CDM prediction from Planck. And to give you an idea, the amplitude of this CMB lensing power spectrum is now measured to better than 2%, so 60 sigma. And that's very competitive with what galaxy lensing measurements are doing. So the point I'm trying to make here is that CMB lensing measurement is on the same footing as galaxy lensing in terms of quality of the data. What you do not have in CMB lensing is the ability to measure lensing from different sources at different redshifts. But what you have is you have a source where there's no photometric redshift error. You know exactly where that source is. Modeling the unlensed CMB is something we can do very cleanly. So the systematic effects that can bias these measurements are very different from galaxy lensing. And so combining the two can be really, really useful. Mm-hmm. 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 That's right. But I think my point is that that width is not an error. So for example, in galaxy lensing, typically you will have as a function of z the dndz, you know, so how many galaxies you have as a function of z. And it might look something like this. And there's a very broad distribution. But the photo z error, I think, is not the fact that the distribution is broad, but the fact that it's uncertain. So for example, is the real distribution of galaxy this, or is it this, or is it this? And maybe this is a round redshift of 1. For the CMB, so you're at redshift 1100, and you're right that there's a width of maybe 80 megaparsec. But the point is that width has no uncertainty to it. It is very well known. So, right. But actually, yeah, thank you for this question, because it also it allows me to talk about something that I wanted to talk about but didn't include in my slides. As you've learned in galaxy lensing, when you have a source at a certain redshift, so imagine you have a galaxy sample here, the lensing that these sources feel comes from all the redshifts below that source. And so similarly for CMB lensing, the lensing of the CMB, this kappa field, is sourced from matter fluctuations at all redshifts below the CMB. And so you have an inventory of all the matter distribution between us and the CMB. And so it's pretty much all the matter distribution in our observable universe. And unlike galaxy surveys, where you can have many different bins of galaxy and do tomography this way, here you have only one. But you can still cross-correlate it with galaxy number density or galaxy shear at many different redshifts. So a useful probe. Another application of CMB lensing, which is quite promising, is to measure the masses of galaxy clusters. And if your galaxy cluster is at a low redshift, you can use galaxy lensing to measure its mass. But if your galaxy cluster is at high redshift, such as some of the ones we find with TSZ, CMB lensing might be your only way. Okay, so this is how we best measure CMB lensing with these quadratic estimators or the full Bayesian methods that we talked about. CMB lensing also has a mean effect on the temperature power spectrum. And so what I've plotted here is the same CMB temperature power spectrum we've seen before. It just looks weird because I've multiplied it by L6 as opposed to L squared. And the reason I've done this is not just to confuse everyone, but to allow you to see both the effect on fairly low L and very high L. And so when you compare the lensed CMB power spectrum versus the unlensed, you see that the BAO peaks get sort of smoothed out. And intuitively, that makes sense because with those deflections due to CMB lensing, sometimes you're making the hot and cold spots bigger, and sometimes you're making them smaller. So you're sort of blurring that acoustic scale. And so the peak look less sharp. And that actually is a problem if you're trying to measure cosmological parameters that have to do with the peaks. You can undo this with delensing to improve your measurements. And then the other dramatic effect is that around L of about 5,000, CMB lensing adds a lot of power to the map. And the idea there is that on very small scales, the primary CMB is actually very smooth because of that silk damping that we talked about. So you have this silk damping, this diffusion damping, and so the CMB on small scales would normally be very smooth. But because you have fluctuations in the matter density field on small scales, in the large scale structure, you have small scale fluctuations in the lensing field, and these get imprinted on the CMB due to lensing. So these are the two effects that lensing adds to the CMB power spectrum. And these effects have been measured to about 10%. So you can think that we measure CMB lensing from the mean CMB temperature power spectrum at about 10 sigma, but we reconstruct it from the quadratic estimator at much higher sensitivity. Okay, so I think given the time, this is all I'll talk about. The fact that there's all these imprints of the large-scale structure onto the CMB, and I gave you that summary slide that shows you how each effect is a product of a number of dimensionless parameters. We've gone through a number of the properties of the extragalactic foregrounds, meaning outside the Milky Way, and galactic foregrounds from the Milky Way. I've told you a bit more about the Sunyaev-Zeldovich effects and scattering effects, and a bit more about CMB lensing. And so I think I'll stop there and be happy to take any questions. Okay.
I don't think the mic is on.
Oh.
Okay, sorry. So I have several questions, and the first thing is about the foreground removal tree. I think you have mentioned the first idea, also the first step actually in the pipeline, I guess, is to mask those very, very bright pixels. And then I guess you will just leverage something like GNUC actually to subtract. So it's maybe not so bright pixels, but actually there should be some residuals in it. So I'm just wondering that what's the case, or how about this kind of residual contaminations in the CMB experiment? Is it like now we know exactly or know very precisely how this residual behaviors, and we can just because
is your question, how do we deal with the residuals?
Yeah, I'm just asking about the strategy.
Yeah. Thanks. Yeah, that's a good question, and thank you, because it allows me to say a bit more about how we suppress these foregrounds. So indeed, one approach for the Milky Way and for bright point sources is to just mask them. So basically, you're saying these are hopelessly bright. I'm not going to be able to either model it precisely enough or remove them, subtract them precisely enough, so I just mask them. So that's one approach, is masking. Another one is to use the fact that you have observed the sky at different frequencies intentionally, because at high frequencies you get to learn about the dust, at low frequencies you learn about the radio foregrounds, and at intermediate frequencies you also learn about TSZ, for example. And so once you have those maps at different frequencies, you can ask, imagine that my goal was to just make the best possible map of the CMB. An approach that's often done is to use so-called internal linear combinations, ILC. And these are saying, I want my CMB map, the ones that I estimate, to be a linear combination of my maps at different frequencies. And I'm going to choose the weights in that linear combination to, for example, minimize the variance from all of these foregrounds. So if you do this, that's the standard ILC, you end up with a map whose power spectrum will have the CMB, and it will have foregrounds reduced by a certain amount that you can roughly quantify, but not nulled. They will just be reduced. In some applications, there's one foreground in particular that you really want to get rid of. And so in that case, you can do a slightly different linear combination. For example, if you really want to get rid of the thermal SZ for some reason, the thermal SZ, you know the frequency distribution exactly. And so you can make sure that you pick a linear combination of frequencies that will exactly null the TSZ. So that's a constrained ILC. It's an internal linear combination where you've added the constraints that you want to null a specific foreground SED. So if you do this, you are sure that you have nulled the thermal SZ, but because the weights you have chosen are no longer the optimal weights in terms of variance, you have a noise cost. Your noise is larger. And then there's like a lot of variations on these internal linear combinations, but that's the broad idea. Another approach you can take is, and that's sort of the baseline approach for a lot of experiments, and for example, it was for ACT as well, is don't try to combine your maps into one best CMB map. Just measure all the auto and cross spectra of all your maps and model them together jointly in a likelihood, including a model for the foregrounds. So you can have a model for how each of these foregrounds scales with frequency. And as a result, you have a model for all the auto and cross of all the different frequencies. And then you let your likelihood tell you what the CMB paraspectrum was. Yeah, one challenge. So in the case of the thermal SZ, we know the frequency dependence exactly. For other foregrounds, we don't. Like a CIB, for example, we have some idea of it, a modified blackbody, thermal dust emission, but it's not exact. And the SCD might depend on the location on the sky. And so there, the challenge is to have a model that's flexible enough that once you include that model in your joint likelihoods, your CMB inference is not going to be biased. And so that's a hard thing to do, and that's something that you might check with simulations, for example. But yeah, that's a big challenge.
Okay. And my second question about the KSZ, actually you have mentioned like the velocity field reconstruction, right? Mm-hmm. So maybe I just missed something because eventually you are just doing something like the stacking. You use a stacking technique actually to do it. Mm-hmm. So I just didn't get how this velocity field plays in there.
Right. So the idea is that the signal itself is proportional to the bulk velocity of the halos. Yep. And so if I just stack my temperature maps at the positions of these halos, the KSZ signal will average out, and I will get 0 in the end. And so if instead I knew what the velocity was for each of these objects, I could take my temperature map and, for example, divide it or multiply it by my estimate of the velocity.
Just like a weight.
Yeah, okay. So as a weighting. So it's a stack weighted by the sign or the actual value of the velocity that avoids this cancellation.
Okay.
And the nice thing with doing this is because you've weighted by something that changes sign and on average is 0, by doing so, you have nulled all the other foregrounds that don't depend on velocity. And so that's why these unique features where some effect changes sign depending on the local property are really helpful to help you extract this effect. Because otherwise, KSZ and screening would still be blackbody SCDs. They turn the blackbody into a different blackbody. And so by using multiple frequency combinations, I cannot distinguish it from the CMB.
Okay, and the screening itself is also a Compton scattering. Mm-hmm. And there's only some effect from the reionization.
Mm-hmm.
Okay.
So it's the same exact effect that's occurring at reionization, except the main effect at reionization that we usually talk about is imagining a uniform electron density that scatters the CMB. And here at late times, we're thinking about a very non-uniform electron density, where if you look at a halo, you have a lot of electrons, and outside you have none.
Okay, and the final question, I think you have maybe give a very quick explanation about how lensing scores the wiggle amplitude on small L end. So can you just explain that again? Because you have mentioned something like, okay, some cold spot may be getting larger and someone just shrink a bit, but I just didn't get how statistically it is to squash the wiggle amplitude there.
Sorry, so the question is about those wiggles?
Yeah, so
or
the
wiggles?
L end, yeah.
Okay. So one simple way to think about it is imagine that I have two patches of the sky that are several degrees on the side. So I have two patches of the sky, and in the difference between those two patches is that this one has a positive convergence, which means the image has been stretched out, and this one has a negative convergence. If I think of measuring the paraspectrum only on this patch or only on that patch versus the average, what I'll see is that, so as a function of L squared CL, here's the normal CMB paraspectrum. In this patch here, where convergence is positive, unfortunately, it means things have been diverging. So the lensing deflection is like this. scales have been stretched to larger scales, and so that means to lower L. And so actually what you'll find is that the CMB power spectrum in this patch looks like this. And if instead you look at this patch where convergence is negative, everything has been rescaled to smaller scales or higher L, you'll have something that actually looks like this. So I'm exaggerating, but what you see is that you're taking the CMB power spectrum and you're sort of wiggling it around and then averaging it.
Mm-hmm.
And so the overall CMB power spectrum that you would measure on the full map is sort of a mix of all those. And because of you take sharp peaks and wiggles that you average together like this, you get a blurrier version that then, dampens the oscillations.
Okay, thank you so much.
Thanks a lot. That was a
Sorry,
very good
I just
question.
have occupied too much time.
So the idea to study all these effects is to extract them and like obtain a loyal measurement of the temperature perturbations or B modes. Is that the idea? Or?
So yes, I think there's two perspectives. One is if you care about the primordial fluctuations, then all these are nuisances. They're all contaminants. They're all stuff that you wish weren't there. And so you're trying to remove them as well as you can. So that's one idea for foregrounds is how can we remove them? How can we suppress them, control them, so we get to see the primary CMB? But the other perspective is that all these contaminants actually contain information about the large-scale structure. And so if you can measure them per se, they are interesting per se. So CMB lensing is an example of something that's interesting for learning about large-scale structure. And I've tried to make the case that those scattering anisotropies also contain useful information because they let you see all the gas, all the baryons that you wouldn't otherwise see.
So we can obtain like observables from that effects.
Yeah.
Yeah.
Mm-hmm. Exactly.
Tem a sessão de Q&A.
Quickly, now, so in principle, you can do the same for lensing in the polarization of E-modes, right?
Yes.
So how is the status now of measuring this lensing on the E-modes? And
Right.
What's the main differences you think are relevant?
Yes, yes. No, thanks a lot for asking, because I wish I had time to talk about this. So there's two things. One is you can just measure the B-mode power spectrum. And so this has been measured, I think from last time lecture, I have a plot with measurements. But yeah, there is a measurement of the lensing B-mode power spectrum. But then the other part of your question is, yeah, using the B-modes to measure lensing. And basically, when your signal to noise is low and you don't have very good measurement of the lensing B-modes, most of the lensing signal to noise comes from temperature only. And so I've mostly talked about temperature. But as your sensitivity improves, your noise goes down, and you start to measure the B-modes well. Then the B-modes become the best way to measure CMB lensing. And intuitively, the reason is because if I have a temperature map, I see fluctuations in it. Most of these fluctuations are just primary CMB, and then some of them are lensing. If I look at a B-mode map, in the absence of R or primordial gravitational waves, that B-mode map is 0. And so anything I see in that map is lensing. And so basically the way you measure lensing with the quadratic estimator is you use the correlation between E and B to build your kappa estimator. Because anything you see in B used to be E modes that were messed up by lensing. And so once your sensitivity is good enough, and that will start to be the case for Simon's Observatory and then SPT, and would have very much have been the case for CMBS4, this becomes your best estimator for lensing.
And is there any information left on the E-maps themselves, or is everything of lensing transformed into the B-maps?
Yeah, no. You can reconstruct lensing from TT, from TE, from EE, and from EB. And so in practice, what is done is you combine all of them together. And right now, for an experiment like ACT, if I'm not saying anything wrong, half of your information is temperature and the other half is sort of all the others that include polarization. And then for something like CMBS4, on reasonably large scales, like most of these scales here, EB would dominate the reconstruction. And once that happens, once EB dominates, you typically also are in the regime where the methods beyond the quadratic estimator also give you a benefit.
Okay, this might be a good time to stop for lunch, but let's thank
Thank you.